Now we have to follow the program. And without my glasses, I have to apologize for it. It's hard to read it. But anyway, I will be the next to have here is Mr. Sergii starting with the impedance of boron and nickel, so silicon micro and nanostructures.
Thank you. Please pay attention to the following paper, the impedance of boron and nickel doped silicon, micro and nanostructures. You can see the authors on the screen. My name is Sergii Yatsukhnenko. Up. Where is laser pointer? Не. Thank you. The main purpose of this work is to study the impedance of silicon microcrystals with the concentration of boron dopant, which is correspond to the vicinity, to the dielectric site of metal in the later transition, and nickel dopant in a wide temperature range from 4.2 Kelvin and frequencies 0.01 to 250 kilohertz. The object of research was silicon silicon whiskers grown by CVD method with vapor liquid solid mechanism. You can see on the figure 1 the schematic growing process of such crystals. The container for growing is divided into two parts, the evaporating part and the part of sediment, when you can see the results of growing. On the figure 2, you can see the experimental study impedance results of the silicon microcrystals doped with boron and nickel with the resistivity 0.01 ohm centimeter. This is the complex dependencies of such crystals are characterized by the presence of the large value of the negative imaginary resistance, as you can see, which gradually decrease with the temperature increasing. In addition, it should be noted that such impedance is described by a complex curve which not observed in the previous crystals and previous studies. There is the three arcs with different radius. These arcs can be distinguished from the general curve. The increase of temperature does not change the nature of curves, but change the number of arcs and their radius. In particular, the disappearance of cirrus arcs and the change of arc diameter was observed at the higher temperatures. The reason of curve changing should be associated with the nickel introduction in such crystals, which significantly change the nature of the frequency dependence of the complex resistance in comparison with the crystals without magnetic impurity. The presence of nickel dopant does not cause the disappearance of Hopin conductance, but change mechanism of it. Confirmation of this assumption is the temperature dependence of the resistance, which you can see on the previous slide. In addition, the magnetoresistance results are also indicate for the presence of Hopin conductivity in wide temperature range. It should be noted that the magnetoresistance dependence is characterized by the presence of negative value, which is shown certain features of Hopin conductivity in these crystals. Such conductivity features on the measurement with the direct current are explained by the mechanism of charge carriers carrying on the twice occupied states, These models explain both conditions of magnetic ordering, the antiferromagnetism, the presence of negative magnetoresistance negative magnetoresistance where the magnetic impurity captures charge carriers localized on boron impurity with different direction of spins, and ferromagnetism in the crystals and weak magnetic fields when the magnetic impurity takes charge carriers localized on boron impurity with one direction of spins. In view of the above, it becomes clear that nickel plays a significant role in transferring charge carriers, since it has magnetic moments which can affect on the charge carriers. The presence of complex form resistance indicates the heterogeneity of the investigated structures, which contain both the silicon and the boron-silicon nickel clusters, which are randomly located. The structural heterogeneity is manifested with the different relaxation time of charge carriers, and as a consequence in a different number of arcs depicted on the figure 2, which correspond to the observation interval of time. Therefore, then an important element of study is the correct selection of the equivalent circuit, which is responsible for the different conductivity mechanism implemented in structural elements of such crystals. Therefore, each element of the structure will correspond the parallel or successive resistor capacitor model, which you can see on figure 5. The parallel model with R3 and C3 will correspond to the low temperature intercluster region of the crystal. R1 and C1 describes the cluster region, and the equivalent circuit of the cluster region, in addition to the parallel model, also contain a sequential R2 C2 model that correspond to the relaxation process. The intercluster region, which represented by R3 C3, presents the crystal without magnetic impurity. The relaxation process may occur to the insufficient energy for moving to the next vacancy, and as a result, the delay of charge carriers within the cluster formed by magnetic moments of nickel clusters. The one of the dominant conduction mechanism is the Hopin conductivity. So a significant freeze of charge carriers occurs at low temperatures. The mode law of Hopin conductivity, which is realized for our crystals, has some features due to the concentration of magnetic features. Due to the figure 6, one can see the investigation of magnetoresistive characteristics for the determined peculiarities of the implementation of Hopin conductivity for such crystals, where you can see the curve with magnetic impurity, silicon, nickel and boron, and without magnetic impurity. It worth noting that the value of real conductivity component has two increasing interval in conductivity, which you can see on the figure 7, which was not observed before in our crystal without magnetic impurity at the frequency range from 10 to 250. Such type of conductivity dependence on the frequency indicates the realization of Hopin conductivity. However, stepping process like this of Hopin conductivity with an intermediate stops, the increasing of conductivity is realized in this frequency range. The frequency increasing leads to the increasing of conductivity, as you can see, and in some interval of curve. The conductivity become a constant value, occurs saturation after the further increasing of the frequency. Such saturation in the increasing of conductivity may be occurred with capture of transferred charge carriers by the magnetic moments of nickel clusters. In this case, direct and indirect interaction is realized through the overlapping d shells orbital of localized nickel atoms will take place. Only a further frequency allows to obtain enough energy to hopping for charge carriers at a distance that exceeds a spatial area. of the effective influence of the magnetic moments clusters. That means avoiding the traps. It should be noted that the dependence of phase shift tangents has slight peaks on the low temperature, as you can see in this region, where we observed the stops of conductivity increasing. These peaks, which 4.2 and 10 Kelvin and 20 Kelvin, may indicate the existence of relaxation process, which is realized due to the action of magnetic moments on the electric dipole formed during the hopping of charge carriers from one impurity center to another. As the temperature rises, our peaks is disappeared, as you can see in higher temperature. Since thermal activation causes the growth of the number of free charge carriers, and the result of vacant places increase for Hopf and twice occupied states, which reduces the probability of the relaxation process manifestation. And my conclusions, and I want to say that we observed the hopping conductance in the impedance spectroscopy. We also testify the presence of the relaxation process in our crystals, and was calculated polarization relaxation time of charge carriers, 7 to 10 minus 4 seconds. Thank you. Okay.
So, all your measurements are carried out at low or very low temperature.
Yes. Yes. From 4.2 to 70 Kelvin. Yes.
Except of theoretical interest
Yes.
in the mechanism of charge carrier. Is there practical interest?
Yes. Our group make several sensors for magnetic fields in a low temperature range.